Let's dive right into this explainer and uncover the sheer engineering marvel behind something you probably have sitting right on your desk, a simple sheet of paper. It takes a staggering amount of water, intense heat, and incredibly precise chemistry to make something we just mindlessly toss in the recycling bin every day. So let's unpack all that hidden complexity. Here is our roadmap. We are going to start with the raw materials, move on to stock prep and cleaning, dive into the wet end, heat things up in pressing and drying, and finally, wrap it all up with finishing and rolling. To put things into perspective, the massive scale we're dealing with here is just staggering. Using Paper Machine 4 as our real-world example, this behemoth churns out writing and printing paper at a blazing 650 meters per minute. That translates to an average production of 230 tons every single day, rolling off a machine gecko that's 540 centimeters wide. Just picture a ribbon of paper over 5 meters wide literally flying past you at highway speeds. But before we get to the raw materials themselves, there is one foundational term you've absolutely got to know, and that's furnish or slurry. Our entire main objective in the first half of this factory is turning dry, raw pulp into this highly diluted, watery soup. We have to make it a super easily manipulated liquid before we can even dream of forming it into a flat, dry sheet of paper. All right, part one, the raw materials. You might think paper is literally just chopped up wood, right? Well, not exactly. Raw cellulose fibers straight from a pulp mill would actually make a terrible sheet of paper on their own. It'd be completely unsatisfactory in both how it looks and how it holds up. Instead, Paper Machine 4 uses a highly specific blend. It uses hardwood pulp, which is amply available in places like India, combined with imported softwood pulp bales, non-wood bagasse pulp, and even pulp from de-inked pulp, which is basically just recycled paper. This blend is constantly optimized based on what resources are available and the economics of the day to give us the absolute perfect base. Moving right along to part two, stock prep and cleaning. So, how do we get from dry bales to that watery soup? It takes 3 vital steps. The whole thing kicks off in a massive 16 cubic meter hydropulper. Imagine a giant industrial blender dispersing those dry softwood bales into water, forming a slurry that's only about 3.5% fiber and over 96% water. Once it's liquid, those fibers go through beating and refining. This is a heavy mechanical action that physically alters the fibers to develop their paper-making properties, basically creating these tiny microcompressions so they can bond together later. Finally, the wet end additives are blended right in. But hang on, before this soup gets anywhere near becoming paper, it has to be spotless. To guarantee absolutely no impurities make it into the final product, the slurry gets forced into a rigorous 3-stage centricleaning process. Our critical first line of defense is the first-stage centricleaner, where intense centrifugal force spins the heavier contaminants right out of our precious fiber mix. Right after the centricleaners, the stock hits its next defense mechanism, pressure hole screens, and these have openings of just 2 millimeters. Any clump or random particle larger than 2 millimeters is aggressively rejected. Only the purest, most uniform slurry is allowed to move forward to the actual paper-making machine. Okay, part 3, the wet end. This is where the magic actually happens. Now that our furnish is perfectly blended and immaculately clean, this watery soup finally takes the shape of a continuous sheet. The pulp is uniformly pumped out of the headbox, flowing over a breast roll and straight onto an internal mesh structure called the forming wire. Now, at this point, it's still mostly water. To fix that, sets of hydrofoils and vacuum boxes situated just beneath the wire immediately kick in. They start this incredibly violent high-suction process of dragging water down and away from the fibers. Plus, there's a vacuum-based duoformer sitting above the wire, sucking even more water out of the top layer, rapidly locking those fibers into a tight web. On to part 4, pressing and drying. Now we are getting into the absolute most energy-intensive part of the whole shebang. We've got a sheet, but actually, scratch that. It's more like a fragile, soaking wet web. As it enters the pressing section, it only has a dry solid content of about 15 to 25%. The sheet is conveyed through a series of roll nips, which you can think of as giant heavy rolling pins. These nips force the fibers into intimate contact with one another, heavily consolidating the structure and squeezing out a ton of water. By the time it leaves the press section, the dry solid content has doubled to between 40 and 45%. But obviously, we still have a long way to go to get it fully dry. Incredibly, to get the rest of that water out, the industry literally still relies on fundamental physics established by a guy named J. Dickinson all the way back in 1817. The paper web is tightly wrapped around a series of cylinders. Inside these cylinders, condensing steam provides an intense source of heat, flash evaporating the remaining moisture right out of the paper. Look at the intense heat transfer going on here. The paper temperature and the evaporation rates just absolutely spike as the sheet moves across the different zones of the dryer section. It's this rapid application of heat at high speeds that forces the last of the water out and permanently sets those crucial fiber-to-fiber bonds. Without this extreme step, the paper would literally just fall apart in your hands. And finally, part 5, finishing and rolling. So the web is intact, bonded, and dry. But you can't just stick it in your printer yet. It needs its critical surface properties. First up, the paper undergoes chemical surface sizing to give it properties like mold-proofing and wick-proofing, meaning your pen ink won't just bleed everywhere. Next, it passes through calendaring rolls. These basically iron out the sheet, reducing its thickness and smoothing the surface. Finally, this endless ribbon of finished paper is accumulated, winding rapidly onto a massive spool known as a Pope reel. Let's pause on that surface sizing for just a second, because the chemistry here is actually fascinating. The paper gets treated with a low viscosity starch solution. To make it, granules of starch are cooked in water at 100 degrees Celsius for 90 whole minutes, which releases amylose and amylopectin. As this hot solution is applied to the paper and starts to cool, it thickens. This is a process known as retrogradation, or setback. The machine slaps on a hefty 30 to 50 kilograms of this dry starch per ton of paper, almost like glazing a giant pastry, and that locks in that smooth, crisp surface you expect from high-quality stationery. To wrap things up, we've got to get this massive 540-centimeter wide spool down to a size a human can actually handle. The giant master reel is unwound and fed into a rewinder, which slices it down into smaller, manageable reels. From there, it's cut down even further into the exact, specific sheet dimensions and grammages, typically between 50 and 80 GSM, that you'd immediately recognize sitting right in the tray of your desk printer. So thinking about those massive 16 cubic meter pulpers, the blazing hot steam cylinders, the exact starch chemistry, all working flawlessly together at highway speeds, it's an unbelievable amount of hidden complexity for something we treat as so disposable. Next time you grab a fresh sheet of paper to jot down a quick note, take a second to appreciate the wild industrial journey that fiber took just to get to your fingertips. Does knowing all this change how you look at the paper on your desk?